So the last class, we have finished up, we discussed recursion, and recursion is actually seemingly simple, at the same time seemingly impossible way of doing things. Challenge yourself to learn it and understand when it is good and when it is not. But one of the main things that we want to accomplish when we write a recursive function, could you close that one of the doors in the back? Is to think of two basic parts of writing recursion. The first one is to decide what is the recursive function, right? So what is the recursion? So for example, it could be that, to solve factorial of n, I wanted to first find factorial of n minus 1, which is something smaller, and then take that result and multiply it by n, right? And the same thing you're going to do with your lab. You're going to decide if you want to solve addition or multiplication, what are you supposed to do? And if you solve it for the smaller part, how are you going to combine it to make the bigger part? For example, we basically had something like, if I wanted to do merge sort of L, I wanted to merge sort left half of L, merge sort right half of L, and then merge them both in, thank you, sorted order and return, right? So basically, I am trying to define how I'm going to solve this problem by breaking into a smaller piece, solving that recursively, and then using the output to find something else. We also did, for example, the Fibonacci number, Fibonacci of n. We said that it was Fibonacci of n minus 1. We have to find the Fibonacci of n minus 1 and Fibonacci of n minus 2, and I need to add them up. So this is kind of the recursive part. So the recursive part basically means that instead of solving the whole thing, you solve a subset of it using the function itself, take the output, and then do something to find the final output. And we said that for some algorithms, this is, even though you can write them recursively, it's not necessarily more efficient. So not everything should be solved recursively, but over time, you will learn when to use recursion, when not. Currently, our main task is to even learn to use recursion, right? But for merge sort, it's very natural. And the algorithm is simple. It's even slightly more efficient because I don't have to keep track of some things. But the most important part of the recursive function is not writing the recursive part, but it is writing the stopping condition. Because if you write recursion that never stops, then this is not a very useful function at all. So the stopping condition is when will you stop? Remember, recursively, for example, I keep calling recursion for n minus 1. Or n minus 2, but I need to make sure that eventually these numbers are going to stop. So you have to have some stopping condition. It could be n equals 1, n equals 2. Why am I making this sound? All right, let's try a different one. Or, if you are counting up, it's recursive with respect to length of n, some sort of deal. All right, I have no idea what I'm doing, but I will try not to do it. So the last thing we were talking about was the Sierpinski triangle. I studied how to say triangle. Which basically is this very basic structure. So I'm going to slowly go here. I have no idea what I'm doing. So to actually draw this triangle, right, I'm basically giving it this x and y location and this length. So then you can draw a triangle by giving the three coordinates. So you can give it lower left, top, and lower right. So to draw a triangle, you basically have to give these three conditions. But you know, to actually draw this triangle, all you need is this and this. And I looked up the geometry a while ago that you know, if it's a 60 degree, you can compute what this is supposed to be. You know, trigonometry is involved. But you know, you don't have to know any of that. I completely extracted all of that out for you. But given this coordinate and the line, you can figure these three out. So what I do is, when I start my program, I draw this first triangle, but I draw it in red. So this whole thing is red. Then I draw a second one by finding the midpoints between these two coordinates, and these two and these two. And I draw a second one with these three conditions, right? So this is what my program does. Oh, you know, I know why. All right, that's why. So let's look at this program. Okay, so what it does is this draw function. Okay, you don't really need to worry about this padding and so on. That's kind of, you know, my little thing. But all it does is when I draw the, when I click the draw button, it says that draw triangles starting from the lower left of x, lower left of y, and this length. So this is really the main function we worry about. So this one is going to draw triangles. It is going to create a polygon with these three coordinates. So this is the first xy, second xy, third xy, and then you tell the color. And then I'm going to find the midpoints that I was drawing there. So I call them mid, right mid, and bottom mid. Okay. So I'm going to draw a second triangle here, but I'm going to draw this one in white, so it will look like there is an inverted triangle inside that one. And this is your fancy trigonometry here. So you can figure out how to do this exactly equal length on three corners. All right? So, and then I basically update this, and I can put a little bit of wait time so that I can see if I'm drawing more things. Okay? So basically, as we have seen, all that it does is draw these triangles. So what I want to do now is to continue adding more of these triangles, but recursively drawing the same exact shape inside these three groups. So what I want to do is take the same shape, but inside this, draw the same thing, and inside this, draw the same thing, and inside this, draw the same thing. And then if I want to go further, I want to do the same, but inside this, draw the same thing, same thing, same thing, same thing, like this. I want to keep drawing this until I am done. Okay? So this is actually an example of using recursion to draw something we call a fractal shape. a lot of fractals are actually all defined recursively. Have you seen fractals? Okay. For example, snowflakes are actually generally fractals, and they are drawn using recursion. So this is the simplest one. So basically, we have the two questions that we want to ask. The question one is, what is the recursive step? Question two is, what is the stopping condition? Okay. So let's think about what is the stopping condition. How would I know when to stop? So there is no natural way to stop. So let's say that I'm going to decide how many times I am going to draw this, right? How many times I'm going to call recursively. And at each point, I'm going to keep track of this. So what I'm going to do is, I'm going to use this thing called depth that keeps track of how many times I'm going to call myself recursively. And in fact, it keeps track of it in this variable called depth. So I'm going to keep track every time I call, what is my recursion, right? So the first time I call, let's say, first time I call, I'm going to have my recursion depth is going to be 1, because I called it one time. And I'm going to have a variable called depth here. And I want to draw my triangles if my depth is less than or equal to self.depth. Then I want to do all of this. Okay. So the point is that I am going to not even execute this function and stop if the depth is actually less than, if the depth is greater than what I want. So the first thing I can do is I can check to see if it actually draws it once, right? And in fact, it doesn't go below 2, so I can't really test that. But that's the first test that I have, okay? All right, now that I have drawn the basic recursion, now I want to actually do a recursive call. So let's write a simple recursive call to draw the same shape inside the top area, right? So I want to, after I draw this whole thing, I want to recall the same program, but to call it on the top triangle. So what is the top left of my top triangle? So the left mid is the left corner of the triangle. So I can actually do the same thing. So I can say self.draw triangle. Did I actually call it triangle? Hey, that's good. Triangles, okay. And I need to give it an x, y, length, and depth. So x is going to be the left mid of 0 and left mid of 1. I already have that. And the length is going to be, I think length is going to be length over 2. Okay, so that says take now the starting position, this corner, and half the length, and draw the same shape inside this triangle. But I'm going to increment the depth by 1 so that the next time I call, it's actually going to be depth 2. And the third time I call, it's going to be depth of 3, at which point my if statement is going to stop, so I'm not going to call recursively. Okay, so let's see what that does, assuming that I did this correctly. So it took the top part and I drew the same thing inside the top part. Let's increment the depth by 2 more, and then see if the same thing works. Right? Increment depth with 1 more. So it keeps taking this shape and drawing it to the top part of this. What if I also want to now draw it on this side, right? So this was, I draw it on the top. Now I want to draw it on this part. Now this part is easy because it's the same x and y, except the length is about half. So I'm going to add a second one, where my x and y is going to be the same x and y of the triangle, except I'm going to have half the length, and then the depth is going to be +1. So now let's try that one. Okay, so I drew 1 here, and I drew 1 here. Now if I increase the depth by 1, it's going to draw it here. It's going to draw it here. Let's see. But it doesn't draw it any of to the right part, because I haven't actually recursively drawn to the right rectangle. Okay, so now let's add this final rectangle here. Triangle. I have some sort of a brain injury, I think. Which is actually not so hard, because all that it is x plus length over 2. Somebody doing something. All right. And now let us try that one. All right, so let's increase the depth. Now what it is doing is it's now drawing the same shape in all 3 corners of the shape, and then continuing on recursively. And if you want to see this in action, this is what that looks like. That's right. And not only that, you see it is completing in the order that I wrote them, right? Because it first does the top, and of the top it does the top part of that one, and the top part of that one. So if I change the ordering, then you will see the same thing, but it will be in a slightly different order. So this is the order that I drew them. But what if I did the left, top, and right? So now it will look slightly different. All right, that's a little ambitious. So now it's doing the left first, and then top, and then right. And of those, it's doing the left and the top and the right. And in fact, we can slow it down for you, so you can see how that's going. So now in the lab, you're going to do something very similar, but much simpler. Instead of drawing a triangle, you are going to draw a plus sign. And it tells you exactly where to draw. So now since I'm drawing triangles, I had to put 3 new triangles recursively. But to draw the plus signs, you will have 4 recursive calls for 1 each corner. And then each one is going to make another recursive call. But the thing that I am doing is at each point, I am using this depth to look at how many times I am actually calling myself recursively. So the first time I call, my depth is 0. The second time I call, my depth is 1. The third time I call, the depth is 2, and so on. And eventually it reaches the depth that I'm keeping track in my program, at which point I don't call myself recursively anymore. That means that recursive call ends immediately, right? So this is what's happening. So basically, every time I call, so the first time I call draw rectangles, triangles. It's a brain problem. My level is 0. Okay. And then this one calls itself recursively. So recursively it calls both triangles. Alright, I'm doing it. This will be level 1. This one will call itself again triangles. Level 2. And this one again will call itself triangles. I have successfully written triangle 4 times. Level 3. Okay. But this one, when I call this, the level is already above my depth, and depth is 2. So this one will return because there is nothing to do. So this one will complete. As soon as this completes, then this one will complete, and this one will complete, and this one will complete. So that's what the depth is achieving, because it's telling you when your program ends. When your program ends, it doesn't do anything, so it returns. So that means that function call is complete. So I don't know what happened with this, but I'm getting a little tired of it. Any questions on this one? I will post this online as an example to you. You may have already found it from last semester. But the last thing we will do today is to work on a new problem. But we will talk about different ways to solve the same problem. And then we will implement them, and we will talk about the complexity. So, within the next few days, I'm also going to put a little primer on complexity, just so that you can refresh yourself. I don't know if we'll have enough time today, but depending on if we have time, I will try to go back through that again. Okay, so we are going to basically solve a single problem, but we are going to solve it different ways, and then we will look at which way is better. And you have been asking lots of good questions about complexity, and obviously complexity is something you will learn in many classes. It's not like this is going to be the one time. And it's not going to be necessarily super easy, but you need to understand that some solutions are a lot worse than others. So our job is to try to figure out what solution is better and why. So because of that, we are going to look at different ways to solve this one problem. And the problem we have is called mode of a list. If I have a list of numbers, I want to find the value that occurs most frequently. Okay? So this is the first thing that you are given. So your problem is find the mode of a list. So sometimes when I give a question, you kind of find that why is this problem not super well defined? Well, the problem is that no problem is super well defined. It is your job to ask questions. You have to ask questions to understand what is exactly being asked of you. Even something as simple as this, there are many different variations. So what we are going to do is we are going to first refine requirements, because there are many different problems, many versions of the same problem, but you may have many different solutions of the same thing. So mode of a list is the value that occurs most frequently. Okay? So ask me questions. What are some questions you might want to know if you decide to implement this? Yes?
What if two values show up at the same amount of time?
Exactly. What happens if you have multiple values that happen the same amount of time? How do I break ties? Or should I return all values that occur most frequently? Okay. What else? That's good. What if we have an empty list? What should I return, right? What should I return for empty list? Awesome. List. Okay, any other questions? Other ideas? So one of the things you may wonder is, do I know what are the values in advance? So maybe sometimes you know what are the values that you expect in the list. For example, if it was letter grades, you know that it's going to be A, B, C, D, E, F, G, whatever. If it is gender, you know already there are exactly 2 values, right? And you may want to know if it is going to be lots of values or a few values, right? So you may have a huge list, but it may only have 1 or 2 values, right? So that's different than if you have a list and you may have, half of them being different values. So it kind of is important to know what are the different values and is there a limited number of them. So, for example, if it is integers and it could be any range, then if I have a list of n values, there could be n different values, right? So if there are n different values, one may appear 2 times and the rest 1 time. That's very different than if you have only 2 values, right? So generally, what we care about is, I would say, expected number of distinct values in the list. And I'm going to say it's m. Okay? So sometimes you know that it is actually limited, or there's an upper limit. It could be at most 2, or it could be at most 3. In that case, if it is limited, then we care because that's what's called a constant. So if m is constant, or we need to know if m is constant or it can vary. Okay? And the other thing we care about is, do we expect m to be as large as n, number of items in the list. Okay. Now this is going to be important as we look at different solutions, but it is important that whether you have this or not. Anything else? So you may also care about things like, what are the values, integer or float? Why do I care if it's a float? If it's a float, I care if what it means for 2 values to be exactly the same, because there's floating point errors. So you want to make sure that if they are within a certain epsilon, maybe I will consider them the same, right? So it could be important which values are considered the same. Okay. So now let's have a single version of this. And I will ask you to try to think of other versions and how you would solve them. So what I have is a list of integers. M is not fixed. I am looking for any value that occurs most frequently. Okay? I don't care which one. I don't need to see all of them. But you can think about, if you wanted to return all of them, if there's an easy way to change my program to achieve this. Okay? So now, possible solutions. So first thing we will do is, we are going to think of ways to solve this problem, but we are not going to write a program yet. We are going to basically think of an algorithm. We will write it in English. Sometimes they call it pseudocode. But as you take more advanced classes like data structures, they actually call Python code the pseudocode. Which is like, it's like tell it how to do it and it will do it itself kind of thing. But, don't talk to those people. So, okay, just now for 2 minutes as a mental exercise, think about all the different containers that you know and whether you can solve them to you can use them to solve this problem. So there are three main containers, right? We have, what are they? Lists, sets, dictionaries. All right. So now think in your mind, okay, don't tell me anything yet, a way to use lists to solve this problem, list alone, a way to use sets to solve this problem, and a way to use dictionaries to solve the problem. And just go through it, and then we'll talk about it. 2 minutes. Just think. And please talk to your neighbors. Talk to your neighbors. Let me hear some noise. Talk to your neighbors. What would you do? All right, so let's think about some of these. And fair warning, I'm going to go a little long today. So we will go till 3:30. So don't start collecting your bags. All right. All right, so what is the list solution? Anybody volunteering for a list solution? Yes.
Okay, so we follow sort the list, and then if the first number is equal to the second number, do something with that, and then just keep going.
Exactly. So sort the list, go through it. If you see the same number, keep incrementing the count and keep track of the maximum somehow, right? That's okay. That's exactly what I want. Okay. So we are going to write the basic algorithm is this, right? Sort the list. I'm going to say sort a copy of the list, just so that I don't want to change it because I'm going to test it. Then go through the list once and keep track of number of times an item is seen and the most frequent item. Okay? Are you with me on this one? By the way, as you get comfortable, this is exactly like the file, count the number of lines and the number of paragraphs, right? This is the same exact problem, okay? Over time, as you solve these over and over, you realize that they are the same. You just have to keep track of whether you have seen this number or it's a new number. It's the same deal of whether you have seen a paragraph break or not. So it's basically very similar problem. Okay, that's why you have done that. So we can actually, before we even implement, we can understand what is the complexity of this problem, because we have to sort a copy of the list. So we create a copy of the list. So let's write that down. Basically, this is order of n, meaning that I have to go through every single item, append it, which is a constant operation. That's order of n. And what is the sorting? Order of n log n, right? All sorting is n log n. Then I'm going to go through the list once, and then I'm going to find something. So there's some if statements. If statements are not going to change anything, but I'm going to go through the list only one time, which is order of n, right? I just go through every item one time, so that's order of n. Now, if you look at this algorithm, it has order of n log n, and order of n. Okay? So when you have these three steps, honestly, the thing that I care the most is the most complicated, the most expensive one. Which one is the most expensive one? Order of n log n, right? That's the biggest of these three, right? Technically, you can say it's n log n plus 2n, but we don't really care about that level of detail. I only care about the most expensive step, which is order of n log n. Okay, so we will write that down. How about the set solution? Do I have a set solution? Yes.
Okay. So I would do for value in the set of vowels, just something like that. I'd go through and I'd count each one of those in the list, make that max. If max is greater than, then set my mode equal to that vowel and set the max equal to that. And then
Okay, so I'm going to use your solution, but I'm going to even make it a little simpler. Okay, but exactly that, right? So for each distinct value, right? So set of L, count how many times the value occurs in L, and keep track at the same time of the max. Okay? As I'm doing this, I'm going to keep track of this. Okay? So first I need to find the set of L. Then for each distinct value in the set of L, I'm going to count how many times it occurs. So what is the complexity of finding the distinct values? You take each value from the list, add it to a set. Add it to the set. Adding to the set is a constant operation, but I have to do that for every single value in the list, so it's order of n, right? So I have to read every value once, but putting something inside a set is order of 1. It's a constant operation, which is great. Okay, so how many distinct values do we have? We are going to use m for the number of distinct values. So let's say m distinct values. So how many times I'm going to repeat this loop? So I'm going to repeat this loop m times, right? For every distinct value. And what is the complexity of counting how many times something occurs in a list? Order of n, because you have to go through every single item and count. So this is order of n. So this for loop here is order of n times m, right? Because this order of n step, I'm going to repeat m times, right? So m, for every distinct value, m values, go through the list completely once, n times m. Okay, so this is order of n times m. Okay, which one is more expensive? Depends on the m, right? This is why we have been asking, is m a fixed value or is it a, a big value? Can it be small? Can it be large? That's what it depends on. Okay, so let's write these two down and then we will go to the dictionary solution. So we are going to have one called the list version of mode. Okay, so I'm going to create a copy of the list. Then I am going to sort the copy. So now I am going to go through every single item in L1. Okay. Now I need to keep track of a few things. I'm going to keep track of my current value, and the current value is actually going to be L1 of 0. Okay. I know it doesn't work when there is less than 0 items. So then I am going to start from 1. And I'm going to go to the last value of L1. Okay, so my current value is L1 of I. Okay. And I need to figure out how many things I have. So current count is 1 because I have 1 value. So if the value that I'm looking at, okay, and let's call this not current value, but let's call this the last value. Okay. So if the value is equal to last value, then I am going to increment the count, right? Because I've seen the same value, so I'm going to increment it. Else, I am going to make the last value the current value, and the last count is equal to 1. Okay. So first, I'm trying to figure out if I can count how many times I have seen something, right? Now, the more important thing is to figure out what the max is. So now your instinct here would be to put it in a list and sort the list, but that's going to add another n log n or m log n thing, right? Instead of that, all I need is to keep track of 2 values, right? So we have the max value and the max count. Okay, so I'm going to start with none, but that's not necessarily better. So let's make this 0. Okay, so now when do I check if the current max is better than the other one is when I've seen a new value. If I've seen a new value, I want to see if the previous value was actually bigger than the current max so far. So before I change this, I'm going to ask if last count is greater than max count. Then I am going to say that max count is equal to last count and max value is equal to last value. Okay? So if there's even a value greater than, if there's more than one value, that will be the first one. Now the one thing you have to keep track of is that the maximum value could be the one that is the last value, right, in the sorted order. So when I'm done, I'm going to do this one last time. So I'm going to repeat this part. Okay, because this is when I change values, but the last value, I'm not going to have this kind of switch, so I'm going to check it at the very end. Okay, and then I'm going to return max value. If you want, you can also return the max count. And the first thing that you have to do is whenever you have a problem like this is to test it, right? And in fact, the one thing that we can do is we can test, for example, what do we call it, mod list. So you can test for a few solutions. So it returns true. What if my maximum value was 3? It should not really matter if it's sorted or not, but I want to make sure that it actually works for any value. Or what if it was the first value? Okay, so it seems to work. Okay, and this is kind of a complex program, but what can you do? So now I'm going to write the Ceph solution. So for item, so I'm going to have maxval is equal to none, and max count is equal to none. And for item and set of L, current count is equal to B. Is there a way I can count in a list? I don't remember. I can count in a list. This is why all right. So if I will find L.count of item, even though this is an order of n solution, the count, since it is in Python, is going to be a fast because it's a compiled method. So if current count is greater than max count, so let's set this to 0, so it's a real value, I am going to have max count is equal to current count, and max value is equal to item. And then I'm going to return max value. Much simpler. So we can test the same things on this one. You really should write actually a test module so it's easy to do. But you can test, and of course it may return different values because of the way the sets work. Okay? So we have one final solution to write, which is the dictionary solution. Do I have anybody for the dictionary solution? Dictionary solution? This area? Yes.
bring up the dictionary and then go to the list, everything that has whose value is a key in the dictionary, you add 1 to that key.
Okay.
If it's not a key, you create a key for it and start with 1.
Okay.
And check which dictionary actually has the highest value.
Okay. I'm all right with that. So for each item in list, so use a dictionary where you have key, a value in list, and value is count of that value. Okay. So go through each item in the list and update counts in D. Okay, so remember the way we do that is this is like this very basic dictionary. This is the same kind of thing you're doing for the homework. If the key is already in the dictionary, you can increment the key. If not, you create a new key and then the count is 1, right? So what is the complexity of accessing an item in the dictionary? It's order of 1 because it's like a set. So accessing a certain item in the dictionary is very cheap. So this part is order of n because you're going through each item, but for each item, the operation that you do is very cheap. Okay? Then, for each key in the dictionary, check the count and keep track of the max. Okay, so I'm going to have an if statement. If this current count is greater than, then that's the max count. This is the same exact part that I've been writing. I'm just going to do it for every key in the dictionary. So how many keys are in the dictionary? M. So this part is, again, for each item, I'm going to have a simple one or two if statement. So it's a constant operation. This is actually going to be order of M. So this solution itself is order of n plus m. If m is very small, then it's just order of n, right? If m and n are similar, it's order of 2n, which is, again, order of n, right? It's a multiplication of n. So this is kind of a linear algorithm, right? So if you look at the others, it is cheaper than the other two, right? But you have to implement it correctly. So let's implement that one. Bless you. Okay. So I'm going to create a dictionary D for item in L, if item in D. So this is the basic way you have to create a dictionary. This is what I told you, that I want you to be able to write this kind of code in the final, right? So if the item is already, so if item is not in the dictionary, that means the first time the dictionary is empty, the first item I see is not in the dictionary, I am going to add the item and I'm going to make its count 1. But as I go through the items in the list, I will hopefully encounter items that I have seen. In that case, I need to just increment the counts by 1, right? So now I have to do the same, but now I have to do the count. So now here's the question that I'm asked 100 times in a semester. There is no ordering to the keys and the values in a dictionary. Then why should I really try so hard? I'm going to use the same exact code that I have been using. So for key in D, this is the count. Okay, if count is greater than max count, then max count is equal to count, and maxval is equal to key. Return maxval. Okay, and you can do the same thing to test. And you should try edge cases. I am pretty sure that none of my algorithms actually do work for the empty set. Well, this one does, but I don't think this one does. No, that one does too. How about this one? That one fails, right? So you basically have to do something else here. If length of L is equal to 0, return. That's kind of a band-aid, but for now, at least it doesn't fail. Okay? So these are basically three separate ways to solve the same exact problem, but their complexity is different. And I actually have an idea beforehand that the list solution is going to be the worst, most likely, and the set solution will depend how many different values that I have. So what I can do is I can test all of that by varying this. So this is my code for timing the algorithm. So, and I am going to time all the algorithms one by one. And I am going to basically do two things. I'm going to change how many items are in the list, so the n, okay, and how many distinct values there are. So if you have very small number, right, and the way that I do that is that I generate values between 1 and m randomly. So this will allow me to control how many distinct values there are. And then you can actually test what the values are. So print, I'm going to print also what these values are so that you can see the difference between them. Okay. So first I created a huge list, right? And did the dictionary take less than the others? Yes? And I expected that, right? And I actually can add a couple more zeros just so that, I don't know if this is going to run, but if you want to see the real action, you can make it much, much bigger. This is probably going to crash my computer now. But maybe that's the end of how much it can do. All right, let's try that. Maybe that's also too large. That's all right. Okay. And this is exactly what we kind of thought, right? We thought that the dictionary will be the fastest, and the set and the list will depend on how many different values there are, since in this case, the number of different values was so small that it was actually fast. In fact, if it's a very small number, you can generally treat that as a constant, so you can get rid of that part altogether. But what if your m was actually not 10, but let's say roughly 1/10 of n, right? So in that case, I would expect that the list and the set solution, well, let's try to figure out what would that be. If I have m is roughly n, right, this is going to be n squared, and it's going to be actually more expensive than the list solution. So I would expect that the list solution in this case to be better because the set solution will actually really do this n squared step. But the list is still doing fairly reasonably. But there's a lot of if statements, so it is taking a lot longer. But the set is probably going to take a while because it is now looking for each value, the whole list, and an n squared solution is always a lot more expensive than an n log n solution, and it grows much, much faster. Okay. while we're waiting on that, so one of the things that you can do is you can think of many other variations of the same algorithm, and some of them are actually given here. So as you actually look at variations, think about how you can keep track of all the values that occur most frequently, or keep track of the top 10 most occurring values, and try not to use a solution that puts things in a list and sorts it. Because when you do that, you're basically creating an additional n² step. You actually now have the power to do this, but in a brute force way. You have to basically keep track of values in a list, and when that list is more than 10 values, you keep removing something. You can think about different ways that doesn't require a huge time. All right, I'm going to kill this, and I am going to knock a 0 out of this one so we can see the difference. Okay. So this way, at least the set solution will have a chance to run. So if you had only one thing you have to remember from CS1, what would that be? N² is bad, right? So N² is pretty bad. Come on. All right, I'm going to have to knock another 0 here. I thought that this would finally finish. All right, let's try one more time. You see the difference? So it actually takes 400 times. It takes a huge amount of time, right? How about the dictionary solution? The dictionary solution always kicks ass, right? Okay, so here's the important lesson to remember from all this. If you use the containers, then you can actually do a lot better, but not all containers will work for all possible problems, right? So you have to think about what are the constraints of the problem you're solving. Now, dictionaries are very powerful, and dictionaries are kind of the most complex thing we have seen. Now, over time, you will learn that you can actually design your own containers, not just classes, but your own containers. And your containers can do all sorts of awesome things. This is why you take data structures, because in data structures, you will actually learn to design and implement your own containers. Okay? So with that, good luck in the exam. And I will see some of you on campus after the finals. Bye.